Hello everybody, and thank you for joining us today for this partner webinar of IDEA StatiCa and ConSteel. Today's topic is steel BIM, advanced approach of structural steel design using Tekla Structures, ConSteel and IDEA StatiCa. I'm András Herbai, I'm your host today, and I'm joined by colleague Dave Kuchera from IDEA StatiCa and Roland Doka from ConSteel. Just for some practical information, control panel can be hid with the red arrow button. Questions or messages can be sent with the chat options. Questions can be submitted at any time. At the end of the presentation, we will answer them. As usual, this webinar is being recorded and will be posted within 3 days on our website and YouTube channel. Just a brief introduction. As you know, today content is focusing on advanced steel design using Tekla Structures, ConSteel and IDEA StatiCa high-level BIM workflow. Our goal in the next 45 minutes is to demonstrate how can you combine ConSteel's 3D structural analysis software and IDEA StatiCa finite element connection design software to deliver complex structures in minutes. Quickly about the agenda. At first, I will shortly introduce you the steel BIM concept. And after that, we have a great customer project which was delivered using this workflow. My colleague Roland will briefly introduce you this project in a live demonstration. After that, we will highlight some unique features of the latest IDEA StatiCa and ConSteel, and at the end, we will finish with the Q&A section. Okay, let's start the presentation with the overview of steel BIM concept. BIM concept has changed a lot in the last decades. Currently, the main definition is that BIM is a data exchange standard for design and construction softwares. Main goal of it is to support the communication between different participants during the whole project to make the process efficient and error-free. In the current practice, BIM solutions are mostly used on high level just in construction stage, cost planning, organization planning, scheduling. But in design phase, BIM is mostly limited to the basic model exchange and clash check. But of course, there is much more in BIM to make our design process more integrated. The main reason why BIM models are not used on the whole design process is the significant differences between the physical BIM model and the analysis model. The BIM physical model contains a lot of information, dimensions, material positions, which are more or less enough for the construction stage, but not enough for calculations. For structural design, especially for steel design, we need a consistent mechanical model. Difference between the physical BIM and the analysis model can be ordered to the following categories: functions, different BIM elements role in the calculation model, topology, different positions and connections of the element, and correspondence of the elements in BIM model and analysis model. In the point of view of analysis model, especially in case of steel design, we can categorize the elements of physical BIM model according to the position of these elements in the calculation. Bearing elements are the subject of our calculations. These elements are carrying the loads. Their stiffness and bearing capacity are included in the calculations. Dimensions and also the position can be changed. Bracing elements are those elements which are actually not part of the design, part of the structure, but they have mechanical effect for the calculations, and we would like to take into account in the structural analysis. In this case, just the stiffness of these elements are included in the calculation. Only the position can be changed. Loading elements are those elements which hand over on loading to the design part of the structure. And only the position can be changed. In this case, and just the self-weight is of these elements is placed in the calculations. And of course, there are some neglected elements or not structural BIM objects such as furniture, mechanics, etc. In case of bearing and somewhat bracing and loading elements, we need extra properties for the calculations, such as releases, stiffness, supports, loadings, section types, etc. According to the role of the elements, there are positions and connections for each. Other could be different in physical BIM and analysis model. As a general principle, we can say that the position of the elements in the BIM model is accurate because this model will be often the base of the manufacturing, but the connections for each other is not defined on member level. But in analysis model, the position of the elements is often approximate, but the connections between the elements are crucial. This difference have a lot of effects on the calculations. The theoretical versus real endpoints of the elements, the position of the loads and the elements and connections, effect of eccentricities, torsions, warping forces, stability, and the connection stiffness. Answer for these issues is the global model-based design. The basis of this procedure is that each calculation and design process is based on the global model, treating the behavior of the 3D structure as a whole. This global model could be the base of the integration of the analysis model in the BIM workflow. This global model contains all of the design connected elements, bearing, bracing, and loading elements, and the legs of the elements is in the analysis model are the same as in the physical BIM model. Position of the elements could be the same as in the BIM model because global model-based design with 7 degrees of freedom finite element is able to handle any kind of eccentricity and torsion problems, and global stability calculation can be done based on this model. And the connection between the elements can be handled with a fully integrated connection design software, which is able to take into account the 3D behavior of structural connections and able to calculate the connection stiffness as well. Okay, and now let's see how this workflow can be used on a real project. We have an amazing customer project which was carried out using this steel BIM workflow. So this structure is a free-from steel roof in Budapest, Hungary. The highest point of it is 36 meters and covering more than 70,000 square meters. Let's look at the used BIM workflow. So the original structure mesh was created with a parametric Rhino and Grasshopper model, which was imported to ConSteel software. Preliminary design and section optimization was done in ConSteel and exported to Tekla. For detailing, meanwhile, the connection were identified based on the global ConSteel model and exported to IDEA StatiCa for connection design. And the final connection stiffness were placed back to the global ConSteel model, and the final global buckling analysis and structural optimization were carried out with this final ConSteel model. And as a last step, the Tekla model was updated. All of the modification was applied on the parallel Tekla model. Okay, so this was the workflow. Now I will be handed over to my colleague Roland, who will present the steps of this project in a live presentation.
Hello everyone, thank you very much for the presentation. So I will start from the ConSteel side. The design process started by receiving the DXF file as which was received that the DXF file was imported, the sections could be applied on the model. So I will quickly throw some sections on it. Sorry. Can you hear me now? Thank you for your notes. Okay, so what we did in this presentation is that we imported the DXF file from what was received from Rhino Grasshopper into ConSteel, and from that point the design process could be started. So as you saw but not heard, I applied sections on the DXF file, and also I have started to place load transfer surfaces onto the structure. So from that point we will be able to create loads on the structure, place loads on the structure. So this is a quite long process. I will skip it through, but I want to highlight that from an early stage of the modeling, the model was exported to Tekla Structures with ConSteel's export function. And what is important in this export function is that not only the model will be exported to Tekla if we click the export button, but also a link will be established between Tekla and ConSteel, with which link the two softwares can communicate and can handle the change management of each of the Tekla model. So we have exported our model to Tekla Structures, and this was performed at an early stage of the modeling, so detailers could start working, and also the design could go on. And how the change management works between the two softwares is very important. So just to show you, I will quickly, for example, delete some members from ConSteel, and also I will change some members in Tekla Structures too. For example, I will choose this member and I will modify its section to something else. Okay, and after this, if we go back to ConSteel, there is a so-called update Tekla Structures function. This is the change management function. So if we click on it, and we could choose if we want to update all of the members or we only want to update just selected members. This is what I'm going to do now, only update the selected members. And what this function does is that it checks the Tekla model and the connected ConSteel model, and checks each of the members in order to define if some changes was occurred in the model or not. So for example, section geometry is one of these things. So cross sections will be updated. Also, if a new element added or deleted from the models, it will be highlighted too. So right now, this is the Tekla model update dialog. Here we can see that right now we have deleted 2 members from ConSteel, while these members are in Tekla Structures with this CFS 355 cross section. And also, as you remember, I have changed one cross section in Tekla, so the Tekla status of that particular member is changed. And in ConSteel, you can see that this is the ConSteel section and this is the Tekla section. And here we can choose if we want to keep ConSteel or Tekla state of these changes. And if we click on the update button, all of the changes will take place right now in the according to the ConSteel status in the Tekla model. So the member is deleted, and yeah, that is how this update function works. Okay, so eventually, after a lot of model changes and a lot of time and efforts, there is the finished model of this project. And the next thing is how the joints were designed. And this is the other big part of the model, because the component-based methods could not be used in this model since there are several unusual joints. So IDEA connection was used to design these joints. How this works in ConSteel, I mean the link between the IDEA connection and the ConSteel, is that there is a function, it's called create joint by model, which can be used to recognize any nodes in the model. And if you click on it, you will receive a dialog where you can, sorry, I will choose another joint, for example, this, because I have a finished IDEA model for this. So I click on this joint, and we can choose if we want to place an IDEA connection on this point. And we can place this joint back to the model, not only one place, but if this same geometry exists on other places of the model, we can place on several places. So I will place it here. And if I click on the end joint placement button, IDEA connection will, of course, start it, and the joint design process can be performed. And what info we transfer to IDEA connection is the geometry and the loadings. These can be updated later in the design process if something changes in ConSteel. And yes, this joint, for example, we have the finished version of it is this joint. So after the design is finished, we can go back to the ConSteel model, and I would like to highlight that all of the IDEA connection joints which are placed on the model can be managed from ConSteel. So we have several joints placed on the model which were designed in IDEA, and we all have listed here, and we can manage them from here. So we can open it from ConSteel and work in IDEA. Okay, and basically that was the BIM links what I wanted to show you in this quick demonstration. I thank you for your attention.
Okay, thank you, Roland. It was a great demonstration. Next topic is the general footing design in the latest version of IDEA StatiCa.
So, hello, everybody. I hope you can hear me and you can see my screen. So, if it's so, I can continue. Something's written. Okay. We still improve and upgrade IDEA StatiCa software, and in the first example, we show you one of the new feature. It's general footing. Now we are able to design structures for heavy anchoring, masts, or more concrete blocks like on the pictures. So let's have a look to IDEA StatiCa connection, how structure for heavy anchoring is designed. As a first step, we will import load effects. So just click on the button load effects, and we can very easily use import function. I prepared forces in Excel sheet, so just only copy and paste them back to IDEA StatiCa and confirm. And you can see that forces were imported. Now we will go on with design. Our structure has been modeled before to save some time, and now I will switch on so-called manufacturing operations, and you will see how is the model created. As a first step, we create stiffening plate. Then we can go on and add stiffening member. In the next step, I will connect member C with stiffening plate. I use for it operation which is called cut, and I will create these welds. Now let's make our model transparent. To see next to operations, I can zoom it a little bit, and you will see in displays and displays or area that welds will be added. So one of them and second of them. Now I can switch to solid view, and we will add second stiffening member, and again its welds. It will be these welds, the same as in the previous stiffening member. So let's do it. And I will add third and the last stiffening member. And now here is the breaking point, how to make general anchoring. It could be made by this operation, bolt, anchor, grid, or contact. You can find this operation when you click on the bottom Add New Entity, and I'm talking about this operation. You can see the dialog. I can switch it on, and you can notice that we add anchor and concrete block. And we can go through the dialog a little bit. In the first part, you can see that we add anchors. If we unroll this possibility, we can add bolts or contacts, but at this time we use anchors. Here you define which plates are connected. In our example, we connect 4 items. In the second part of dialog, it is about fasteners, size of bolts, bolt grade, anchoring length, or you can switch or choose if you want straight anchors, or if you want to use washer plate with shape circular or rectangular. And in the last tab for this dialog, we can choose if we want to connect or anchor to new block or existing block, and to which plate or plate member this anchoring block will be related to. So for us, it's stiffening plate number 1. So the same I can do for the second anchor, third anchor, and the last anchor. And finally, I will add stiffeners for stiffening members. So let's do it again, transparent, to see it in better way. And we add 1 stiffener, second stiffener will be here, you can see. And we can switch back to solid, and last 2 stiffeners, and that's it. Our connection has final design, and we can run the calculation. So let's do it. Nonlinear analysis was started, and in few seconds we will see the results. Yes, that's it. We can go to the check. As a first, we can see summary of the results. We can see utilization ratio of each item plates, anchors, welds, concrete block. And IDEA StatiCa offers you various kinds of results. I can show you only a few of them. You can display stress, you can display mesh, deformed structure. We provide for you bill of material, and of course a report. This report is fully editable. You can add pictures, or you can replace pictures, you can add whatever you want. So it was my first example, and now you can continue, Roland.
Thank you, David. It was great. So the next topic is the global blocking analysis in case of complex steel structure with ConSteel. So Roland, please.
Okay. Okay. Can you see my screen? I hope you can see my screen and hear me as well now. So I will continue with the global buckling, the global stability check. How can you do that in ConSteel, and how was it done in this particular project? So there is basically two options to check the structure, if the structure is adequate for global stability or not. The first one is the Eurocode's general method. What it does, it calculates alpha critical load factors, so-called elastic critical load factors, which is then later used to calculate structural slenderness and the reduction factor. And with this reduction factor, the cross-section resistances will be reduced, and this will give us the utilization of each section for global stability. So I have a model for which I already have first order results and buckling and sensitivity results, and I will explain what are those things. At the buckling results, each of the combinations are calculated, and for each combinations, an elastic critical load factor, alpha critical factor, is calculated. For example, 3.34 in this case. This buckling shape, as you can see, is this kind of global buckling shape. And so this 3.3 factor should be used to evaluate a structural slenderness later on, and the reduction factor. The main problem here is that not all members are affected with this kind of stability loss, only certain members in this region of the structure. So this is a unique feature of ConSteel only, the sensitivity function. This is basically shows that in this buckling shape, which are the relevant members which are affected with this buckling shape. So if we click on it, we will see that in this shape, these are those members which are taking part in this buckling shape. The next step is the global, and of course this is performed on all of the buckling shapes for each combination. And if we go to the global checks, where we can start to evaluate the global stability resistances, we will see, and I already calculated it, but we will see that ConSteel filters down all of the members, and we will receive a graphic where we can see that for which member what kind of elastic critical load factor was applied. And this is done for each load combination and for each buckling shapes. So for the second load, the calculated load combination, only these members are affected with stability loss. The other ones are not. And also here we can check the slendernesses of these members. So as you can see, the calculated slenderness for this member is 1.26, and for the other is this different. And what are gray in this graphics, they are not affected relevant for stability design. So this is the first method, what can be used to evaluate the global stability. The second one is the imperfection method. The imperfection method, I have a model for it. It's the same model, of course, and I have calculated the same combination. So we have a first order, a buckling, and the sensitivity analysis performed on this model. And the imperfection method says that if the necessary imperfections are taken into consideration on the model, a second order analysis and a cross-section check based on this second order analysis can verify the global stability resistance of a structure. So in ConSteel, all kind of global imperfections can be applied, but what I want to highlight, and it's a unique feature also, that we can apply buckling shapes as imperfections. So how we can do that? I have buckling analysis results here. So as you can see, again, the first buckling shape is this kind of buckling shape. And in this buckling shape, this is the dominant part of the building. And the most relevant members, of course, the most red ones. So basically, these are those parts which are relevant in this buckling shape. One moment, please. And if we check, this is basically a half sinus wave. So when we apply an imperfection, it is always has to be known that what will be the amplitude. In this case, we have quite easy situation because this half sinus wave, the length of this half sinus wave is about 20 meters if I go back to the structural members tab. So I will apply this shape as an imperfection by simply clicking the right mouse button and click on apply eigenshape as imperfection. So I will create a new imperfection group, and I have to define the value of the amplitude because I know the equivalent length of this sinus wave. We will go to this three dots button, and here, this is the first option. We will set the equivalent length of this wave, which is about 20 meters. And because this structure is made out of cold form sections, we will use the L over 200 initial bow amplitude. And then we will receive that the amplitude should be 100 millimeters. Okay, and we will store this imperfection in this global imperfection group. What is a unique feature, I think, in ConSteel, that we can stack over different kind of buckling shapes as imperfection onto each other. So as you can see, there are more buckling shapes, not only one, but more, with a different kind of buckling behavior. So for example, the third one with a relatively low eigenvalue is this kind of buckling shape. So what I will do, I will stack onto the previously defined imperfection by simply clicking on the relevant member, apply eigenshape as imperfection, but now I will automatically evaluate the value of the amplitude by clicking on this three dots button and click on this option of this dialog, which what it does, it collects all the necessary information from the analysis results, and then eventually it will give us the design value for imperfection amplitude for the shape of this buckling. So it is 107 millimeters right now, and if I click OK and OK again, it will stack onto the other one which I have created previously. And if I go back to the loads tab, I can check that there are currently more global imperfections taken into account. I can create several ones, and if I want, I can deselect and select them for the next analysis run. And if we apply these imperfections and run a second order analysis, we will only need to calculate a cross-section check when we reach the design phase for the structure. So don't need to run the buckling check. Okay, and that is what I wanted to show you.
Okay, thank you, Roland. We have two more topics highlighting two unique features of IDEA StatiCa, the local buckling analysis and the connection stiffness. So David, please go ahead.
Hello again. I hope you can see my screen now.
Yes, we can.
Again. Thank you, Roland, for interesting example. So we can continue. Now my second example is about stability analysis in joint. Our software can help you with stability analysis of your connection. Buckling analysis is one kind of analysis we provide for engineers. And IDEA StatiCa connection is able to perform linear buckling analysis and provide user with a buckling factor. Now let's open model joint in IDEA StatiCa and see the workflow, how we can do it. So I can open. You can see this is our model. Our structure has been modeled before and has been already loaded. You can see how does it look. It's loaded with pressure force. We can run the calculation. Just click on the button calculate, and again non-linear analysis was started. But you can see that here is info about buckling, that it wasn't calculated. So we have results without buckling. So here's the question, how to run buckling analysis. It is very simple. Let's go to the calculate button and unroll it, and we can see buckling. Let's start it. And now buckling analysis was started. And you can notice that one button was added. Let's click on it. And now we can see results for buckling. IDEA StatiCa provides buckling factor and buckling shapes. We can see first buckling shape, second buckling shape, or third or next. And now is the question how to evaluate buckling. According to the code 1993 clause 5.2.1, the limit value for factor is 15. So in our example, we can see that here is a factor lower, and it means that our connection didn't pass buckling analysis. So that's the reason why we recommend every time check the buckling results. So please do it. And now I can continue with the last example. It's about stiffness analysis. According to the code 1993 clause 5.2.2, we can classify the behavior of the connection to three classes: rigid, pinned, and something between. It's called semi-rigid. First two are widely used, and every engineer knows its behavior, but in real construction, the majority of connections are just semi-rigid. And for most engineers, it could be a mystery how to solve it. So IDEA StatiCa connection can help you and provides the initial stiffness and a lot of other information. Maybe you have question why to use it. Here we made for you a simple example. It's a rigid frame with a linear load along the length, and we can see results for rigid connection and pinned connection. It's well known for all of you. And if we add flexible hinges to the ends of the beam with a certain value of flexibility, and we recalculate project, you can see that load is redistributed and the values of internal forces are different. We can compare that moments decrease under the in the place of the supports and moment decrease. And the flexibility of connection has a major impact on the internal forces. So when you use stiffness, some initial stiffness, and you use some flexible hinges, you can help the structure and you can help yourself with designing joints and connections. Now let's move to IDEA StatiCa, and I will show you workflow for stiffness analysis. Here is our connection. We don't have to create all manufacturing operations. We can go to design and use so-called templates. Click on the button template, and here is template manager. I click on apply template, and just before I saved the template, so it's this one. You can do it for every connection. You can use it with connection with similar geometry. And now I click on the button apply. I have to choose only size of the bolts and grade of the bolts, so let's do it. And you can see that our structure has final design. Now let's click on the button project items. Because we won't preserve this project item, we will copy it, and here we redefine stiffness analysis. For stiffness analysis, sorry. Now we will go back to geometry, and we have to choose which member will be analyzed. You can see that now it will be member B1, but you can choose member B2 if you want. And that's all. We can continue with check and run the calculation. Now the calculation will take more time because at first stress and strain analysis is done. So meantime, I will describe results. As a result, you will see similar diagram, and I can explain to you what does it mean. The green curve represents dependence of bending moment on rotation. You can see level of design load. You can see limit value of capacity of connection for 5% equivalent strain for plates and 2/3 of limit capacity. In the intersection of this green curve and this limit, we receive point, and we can use this point to define the line. And tangent of this line is our value of initial stiffness. I hope that our example is ready. Yes, it's already calculated. And here on the card, on the button rotational stiffness, you can see the similar graph as I explained before. And under the graph, you can see other useful information. You can notice, or you can see the classification of the joint. Now it's rigid. You can display limit value for rigid joint or for pinned joint. This is value for pinned joint, and rigid, it's rigid, so we can see it. You can see loading moment, bending resistance, initial rotational stiffness, and other information. So it's the last example, and I can give a word back to András.
Thank you, David. Thank you. That was a great demo. So okay, for now, we are almost done with our presentation. We are going to answer a few questions shortly. Our colleagues are just going to have a look at your questions, which have been coming in. In the meantime, I would like to ask to fill out a short survey right after the webinar. And if you want to trial, please visit our website, IDEAStatiCa.com and ConSteelSoftware.com, and the recording will be sent out in 3 days, maximum 3 days to your mailbox. Okay. So you have submitted your question to us. We have a few. So the first question is for David. Can you show us how to model more concrete blocks in one joint, David?
Yes, I can show you. So I will again make myself presenter. Okay. I have one example, so I will open it and show you how does it work. I hope you can see my screen. So let's switch to design. This model has been just modeled. Again, I will only switch the operation, and you will see how it was done. So I will switch the first operations. And here is again the breaking point. It's the same grid, bolt, anchor, contact. And you can see that at this time we connect only one item, and we created a new block. And now we want to add some other block. So we will continue in our connection, and on the opposite side we will create the same structure. And you can notice this item, it's similar as the first, and I can switch it on, and you can see that other concrete block was added. We can have a look at it. It's grid 1, this is this one, and you can see it's related to plate, base plate 1, it's this plate, and there is a difference in this operation. It's quite same, but it's related to second plate, base plate number 2, which is this one. And I can continue in the same way in our connection, and you can notice we will add the third concrete block, and we can add the last fourth concrete block. And this way you can play with geometry of the connection. You don't have to use more concrete blocks. You can use one concrete block and make there more anchoring points. So I hope it was a good explanation for you. How does it work?
Thank you, David. Okay, we have another questions about ConSteel. So, in case of global buckling analysis, is it not necessary to deal with buckling lengths and other factors? Roland, can you get it?
Yes, I don't think I'm a presenter, but it's not a problem. Basically, the general method uses global buckling shapes to evaluate slenderness. So it is not necessary to define the buckling lengths because it is done automatically by ConSteel's analysis tool.
Okay. So thank you, Roland. So, okay, I think we are almost done with our presentation because our time has gone. So the questions what we did not cover now will be covered over on email. So now I would like to thanks everyone to attending our today partner webinar. I hope you enjoyed and learned in this presentation. So thank you very much, and goodbye.
Goodbye.
Goodbye, everyone.